going to want to be in this path in your workspace. So we want to be in the Pyranda Rayleigh-Taylor directory. Now, if you look in there are many different YAML files in here. So these are all different kind of Maestro or Merlin experiments that we're going to be playing around with. The one we want to look at first is this Rayleigh-Taylor overview. So we can just open that up and can look at a few other things that we didn't cover in the slides. So if you want some variables that are not like parameters, so basically just kind of constants or scalars, that's where you can use this kind of env block here. So we define a bunch of kind of fixed parameters in this particular instance. So we fixed the mesh resolution of the study. Turn that off. So in this case, I'm going to shrink it a little bit to 32 just so it doesn't take quite as long, because these models can be a little expensive. There's one more special token hidden here. So this output path is how you tell Maestro where to store things. So it's going to create this RT overview studies in your current workspace and then dump every instance of your every experiment you run in there to kind of isolate things and make it easier to clean up. Additionally, there's some dependencies that we're taking advantage of. So these are things you can tell Maestro to do before scheduling any jobs. So in this case, we're telling it, look for this Rayleigh-Taylor Pyranda model, make sure it's there. Similarly for the Python executable, because we can't do anything without that. So, and we'll see that in the log here when Maestro checks that. But basically, this is an easy way to just catch early dependency failures before you throw 1,000 jobs into the queue. And then the batch block is part of how you control the launcher token. So this is where you tell Maestro what kind of scheduler you're going to be running on. For this demo, we're going to be using Flux, because we can just start that up locally really easily. And that setup script should have turned that on for you. We can test that out.
Actually, it didn't, Jeremy.
No?
So you need to run it by hand.
Okay.
Yeah.
All right. These are just this is just some extra args that we can pass to Flux in particular that we're using for this particular instance, but usually you don't need to do that. I think there's one other. Yes, so here's where you specify the resources. So you can parameterize the resource requirements for each step independently. So we're tell it like the wall time. We're only specifying processors, so this is equivalent to little n if you're familiar with Slurm. So it's just the number of tasks. And while we're not doing it, you could say put a token in here and actually parameterize that if you wanted to run many different sized steps in the same instance. But we're not going to do that. Also, to make sure the git pull worked, so the thing that I fixed is it used to have this cycle here. So if you open up your spec and you see that, just make sure that's gone. Otherwise, all of your steps will fail. And yeah, I think that's it. Okay. All right, so if you want to test if your Flux instance is running, you can just do this Flux top. So that'll kind of bring up this nice little dashboard that shows all your resources and whatnot. So if that doesn't work.
And the command was flux start -s2.
Yeah, I'll type it in real quick. But
yeah, thanks.
Get out of this and just press Q. It's just like a pager, so you can exit it real quick. But yeah, if you do need to start Flux, you can just use this command here, and that should get you going. That will drop you into a new shell, so beware. Anything you start in there will also die when you turn Flux back off. All right, I can't see chat right now, so if somebody's asking questions, please
There is
interrupt.
no question right now. Thanks, John.
Okay. All right. Just verify we got. Nope. Just verify Maestro is there, so we're all good. So Maestro does have its own kind of help output. So there are 3 main commands here. Run's the first one we're going to be using, so that'll kind of read in your YAML spec, build your study, and launch all the jobs. And it'll also launch a background process that manages those jobs for you. So you don't have to stay here and babysit everything. It'll give you your terminal back, and you can go do other things. Now there's cancel, so if you want to cancel a study, you can use that and point it at the workspace that I'll show you in a minute when we create it. And then each subcommand also has its own help, so there can be some useful options in here. All right, and the main one I'm going to use here is this sleep time. So by default, Maestro goes to sleep for 60 seconds. So after you launch it up, it'll kind of do a little stuff and then sleep for a minute, and then wake up and do check jobs and see if any are ready to schedule. So it's set large, so you don't clobber the schedulers. Slurm particular doesn't like it if you're hammering it every second with a lot of requests. But since we're not there and we have kind of a nice little local Flux instance, we can abuse it. So we can be impatient, get immediate results. So I'm going to give it the position argument of that Rayleigh-Taylor overview experiment. And we'll add the -s. Let's give it like 5 seconds or something. It should be fine. So that'll pop up a lot of info here. So it'll kind of create some directories in here. Some of the more important ones is if you're using dependencies, that'll all show up here. So it'll say it's acquiring those files. That's telling you it found all the supporting files that we requested. And then it'll prompt you if you want to launch. I'm going to say yes. And it drops you back into your terminal. But it also created this kind of RT overview study. So every instance of this study you run is going to dump a new timestamp directory in here. So it's going to be kind of the format here is, apologize, the blue font there is really hard to read, but so it does the study name here, and then it appends a timestamp to it. So you can tell Maestro to run several different experiments consecutively, and they won't clobber each other because it's isolating everything into these little workspaces. And the other 2 commands just take these workspaces as an argument. So let's say Maestro status. And that'll give a nice little table of what's going on in there. So you can see several of them have already finished. A couple of these simulations are still running. And then the post-process step is kind of waiting to run. And there's some extra metrics in here. So elapsed time, that one will typically disagree with runtime because it takes into account how long it spends sitting in the queue before it can launch too. So, if you're using us on a shared machine, oftentimes it's going to sit in the queue for a while before it actually launches. And there's also some additional kind of options. So if you want to see what parameters are associated with those particular steps, which can't really fit in the previous layout, there's this -- layout narrow option, so this whole thing here is a step. So it'll give you the actual workspace. So it Maestro will create a workspace for each individual step. And then this one also prints out the parameters and their values for you. So you can potentially get a little more human readable version of this, particularly when you have lots of different parameters. This name gets a little gross and or needs hashing. Okay. So I think that's about it there with this one. Let's see if it actually, yeah, it looks like it finished. So you can just open up the output here. Oh. So you can see my, yeah, thanks, Brian. So I'll just open up the image that we just created here real quick. And that's just kind of the recreated the outputs of our study. And we are letting the initial conditions float, I think. Well, I might have generated them with a different initial condition because this does look a little more extreme difference between the single mode and multi-mode. But you know, if you're playing around with this offline, messing around with the seed parameter, you can get some pretty wild variations between these two. All right. Any other questions before handing back to some slides? All right, take that as a no. So okay, the next, so that was just kind of that's just a little overview study that's kind of demoing what Rayleigh-Taylor does, what Paranda, how Paranda works and everything. But I think for the remainder of the studies, we're gonna expand our process a bit and add some more steps so we can do some UQ kind of modeling of this phenomenon. So we're gonna kind of change the study or the experimental process here. So we're gonna add some more individual post-processing steps for each simulation. So we can see we'll have one of those for each of the run Pyrandas. And then we're also going to have some more cumulative or funnel step kind of post-processing and then some kind of inference. But because our compute instances are a little limited, we're going to do a little crowdsourcing. So we're going to switch gears a little bit to doing things with Merlin. So I think hand that off to Brian if you're ready to go.
I am ready to go here. Just a sec. Oh. Okay, can everyone see this? The screen?
Do we want, sorry, Brian, like, do we want
Yeah.
Renee to quickly explain what the UQ is about?
Yeah, we can do that. Oh, yeah, that's probably what this is for.
I think, yeah.
Hey, do you want me to just keep sharing my screen and you can talk over this?
Yeah, I can just talk with this slide. Okay. Okay, so like we mentioned before, we're going to demo an uncertainty quantification or UQ study today with the data from Pyranda. And our goal is to understand the uncertainty or the variability of the mixing width layer that Jeremy showed. Our sources of information come from the physics equations in Pyranda simulation and from some experimental data that we saved. So actually, our experimental data is just this Pyranda simulation run at a higher resolution with some noise. We saved that to use, so we already ran that. And then we can use Bayesian inference to update our prediction of the mixing width with the more accurate experimental data. So in our UQ study, first we'll generate a large amount of data, and Trada will tell us where to sample. Merlin and Maestro will execute the workflow, and the time series curves and metadata are saved to a Sina database. And then next we can fit a surrogate model to the simulation data, and that will allow for faster inference. And then we'll use IBIS and pSwade to do the Bayesian inference that will help us understand the input and output variance. Okay, so because our instances are not very big, we're going to use Merlin to take advantage of all of our instances to distribute the work across them. So, okay, go ahead, Brian.
Okay, great. Thanks, Renee. Right. So with Merlin, as was mentioned earlier by Charles, Merlin's built as sort of an extension to Maestro. And so under the hood, we are running Maestro. And so how it works is Merlin has a nice producer consumer model. So there's 2 steps that you'll need to do to run a Merlin workflow. And so those steps are Merlin run, which is what I'm kind of showing here on the screen, and then Merlin run workers, which I'll touch on the next slide. And so with Merlin run, what we're doing is we're taking that YAML spec that similar to what Jeremy was just showing. So we're taking that spec and sending it to Merlin to parse it and send the task to the server. So what's going on behind the scenes is Merlin is using Maestro to generate the DAG to tell us, which steps depend on what and what to run first and all that. And then it's taking that DAG and converting those tasks into Celery tasks. And those Celery tasks are then sent to the central server, and they exist on different queues within this server. And they'll live here until we spin up the workers to process the task there. So that takes us to the second step here, and that's running the workers themselves. So again, in the YAML spec, you can define exactly how you want your workers to behave, how many to spin up, and so on and so forth. So what you'll do is you'll typically, with like an HPC environment, you'll get an allocation on the high performance computer and then run your workers there. So your workers will then live on the HPC cluster and can communicate with the server to execute tasks on this cluster. In our case, for this tutorial, since we don't have a full HPC cluster, we're just going to be spinning up workers on the current instance that you're running on. And so I'll touch on that in a bit when I start talking about the workers in the spec file. So putting it all together, we get this nice producer consumer model where we have run workers that consume tasks from the central server, and then Merlin run produces tasks on the central server. And so what we see here is these workers, not only can they pull tasks from the server to execute, they can also push new tasks to the server. So you get this nice communication going between the two. And this actually enables iterative workflows with Merlin, which if I get time, I'll touch on at the end, but just know that is possible with Merlin. So for now, let's go do a little bit of a live demo. So let me get out of here and we'll go back to the AWS instance. And so again, let's see. So we have all of these YAML files here. The one that we're going to focus on for this tutorial is this Rayleigh Taylor AWS prebuilt venv flux merlin.yaml. There's also an iterative version right here, which again, I'll touch on later, but if you want, you can go explore that on your own time if I don't get time. Well, actually, before we go into this, I mentioned that Merlin requires a central server to run. And so to save us time, we actually set this server up for everyone. And so what we're going to be using is a Redis server as both our broker and results backend. So if we take a look at it's in the home directory under the .merlin app.yaml file. This is just the default location that Merlin will create this for you. This file, this app.yaml, holds settings on how we connect to the server. So if we take a look at this, we have a broker section, and this is just all the information needed to communicate with the Redis server that we have alive. And then the same is down here in this results backend. I meant to clean this up. We actually don't need any of this for this tutorial. That's just some other stuff that you can do with Merlin. We're going to ignore that for now. So just focus on the results backend and the broker sections here. And so as you can see, we provide the name of the server. So this could be Redis or RabbitMQ, a path to the password file, the port we're running on, and then the actual server itself, which in this case is hosted here. Can I make the font bigger? Yes, I can do that. Is this okay?
If you can do one more, maybe.
More?
Yeah.
Okay.
My old eyes works better.
Yeah, that's fine. Okay, great. So yeah, so these are just the settings for how to connect to the server, and then the same is for the results backend, just with one or two little changes with the database number and encryption key, which is sort of a behind the scenes thing that Merlin will handle for you. So now with that app.yaml, we can check to make sure that Merlin's connected to the server by running this Merlin info command. So if we do this, we should hopefully see some OK messages right here. So if anyone's not seeing that, please let us know now before we get too far. And in the meantime, I need to start my Flux. So if you haven't already, you should also start the Flux instance. Okay, I'm not seeing anything pop up for me. So then let's go ahead and take a look at this YAML file. And I can put this in the chat so everyone gets the right one. Actually, let me move my chat. Sorry, it's in the way right now. Okay, so if we take a look at this YAML file here, let me scroll down a bit. We'll see that first, we have the same steps that Jeremy was just talking about. So we have our run Pyranda step, the post-process step, which is right here, the plot all step, where we're going to be plotting the results from the previous steps, and then we have our UQ step with Bayesian IBIS. So similar to Maestro, we can still have our global.parameters block. And then on top of that, with Merlin, we get something new here where we can actually run samples. So in the Maestro study, we had a third parameter here called seed that was just static across all parameter sets. So it was 17, I think. With Merlin, what we're going to do is we're going to vary that a bit. And so we're going to use a third-party library called Spellbook, a Merlin Spellbook, to just generate a few new samples, and these will act as our seeds for the study. So what this is doing is it's running the Spellbook command, generating an n samples, number of samples. This is just 2, I'm going to tell you now. It's defined as a variable up top right here, n samples. So then if we go back down here, this is just creating 2 samples, and it's saving it to a file called samples.numpy. And this will live in the Merlin info directory, which I'll touch on in just a second. And so with samples, we can run them alongside our parameters. So as you'll see here, we have this seed sample, and then we have our parameters, the velocity, magnitude, and the Atwood. And so what this is going to do is, here, let me jump back to the slide. When we run this, we're going to get an output directory like so. So as Jeremy showed, you get the name of the study and then the timestamp directory. And that's going to, in Merlin, that's going to create a Merlin info directory and then subdirectories for each step. Merlin info will just house general info about the study that you ran. So it'll save the exact spec file as well as samples and so on and so forth. In each of these run directories, so the run Pyranda one will have subdirectories for each parameter set that we ran. So that's what this first level is right here. And then below that, we'll have subdirectories for each sample that was ran. So that's, in our case, we're running 2 samples. So we'll have the 00 and the 01 directories. And that will hold true across all parameter sets here. And then in these subdirectories, we'll see all the files that are generated by whatever we told the step to run. So then let's go back to our study here. I think with Merlin, sorry, I'm jumping around here. Not only can you generate samples, we also have these workers, which I touched on earlier. This is the area in the spec file where you're defining what to do with workers. So in our case, since we are running on AWS instances that aren't very large, they only have 2 cores per instance, we can only spin up 2 workers per instance. So that's what this concurrency value is. So we're only going to run 1 worker with two instances of that worker. if you were on like an HPC environment, maybe you could spin up more than one worker. So you could have a worker for your simulations and a worker for your steps that aren't running simulations. So what you could do there is you could drastically up the concurrency to take up, maybe the entire node that you're on in the HPC environment. And with these workers, you can also specify which steps that they should watch. So for instance, the sim worker could watch the run Pyranda step, the non-sim worker could watch the rest of them, and so on and so forth. So with that being said, let's exit here. Let me think, is there one more thing I want to touch on? So for this study, actually, what we're going to do is we're going to use something called a pgen file. And so you can do this in Maestro too. And so if we take a look at the simulation pgen.py, what this is going to do is it's going to allow you to, a way to have more flexible and complex parameter generation. So what you do is you can create a file just like this and pass it to Maestro or Merlin when you do the run command. And so this allows you to, that Atwood and velocity magnitude, we can generate this on the fly programmatically here. So this is just using NumPy to create two arrays that we're passing in as the values. So now what we're going to do is we're going to take this study and we're going to actually run it. So with Merlin, like I said,
Brian, before you run, you need to set up, like make sure you clear up you need to run the setup and reset study script.
Is that right here? Okay, so then let's do that. So we'll run this. Charles, do you know if everyone needs to run this or is it just me?
You should be enough because, but everybody should run it anyway, it doesn't hurt.
Okay, yeah, so everyone run the script. Just to make sure everything's clear.
Yeah, none of leftover from over.
Right. Okay, and so let's see here. So back on my slides, what I was showing was there's two steps to run for Merlin. So there's Merlin run, and then there's Merlin run workers. I'll be the only one that needs to do the Merlin run command because everyone has access to the same server. So for this step right here, this one command, you don't have to follow along. I'll be the one to execute this. And so let me grab the right spec file. And so we'll pass in the pgen script. Well, actually, first off, we're gonna up the number of runs. So what this is gonna do is it's gonna modify the variable within the spec file. So this nruns variable would set to 15 currently. Since there's a decent amount of us in here, I'm gonna up that a little bit so that we have more parameters in this study. And so we can do this from the command line. So I'm gonna up the nruns to, I don't know, let's say 40. And then we can pass in the pgen script here. And so what this is gonna do is it's gonna generate that DAG, convert it to Celery tasks, and send those tasks to the server where they'll live on queues there until we spin up these workers. So if everything runs properly, which it does, it'll say converting graph to task, launching tasks, and then it'll give execution back to us. So from here, the work is now on the server, which we can check with QInfo.
And everybody can run that.
Everyone can run this, yes. So we'll see that there's 80 tasks on the server. And you might be wondering, well, if we ran 40 runs, why is there 80 tasks? Well, it's because we have two samples. And so the samples are run for each parameter set. So 40 times 2 is 80. So it makes sense to see 80 tasks on the server. And you'll also notice there's no workers running yet, and that's because we haven't spun them up. So from here, now we can actually start the workers to process the tasks. So it's the same command as run, it's just Merlin run dash workers, and then you'll pass in the YAML file. So if everyone that's connected and able, if you can run this.
Can you copy that line into the chat?
Yeah, I'll copy it in the chat. It's kind of a long one.
Yeah. People will be easier for them.
Here.
Thanks, Brian.
Yeah, of course. So what this is going to do is it's going to spin up Celery workers, and they're going to start pulling these tasks for execution. And Charles, do you want me to run this on the main instance? Or do we need it open?
Sure, just so they can see the output in case.
Okay, yeah. So when we run this, it'll start reading, and then you'll see, let me scroll to the top here. You'll see this Celery thing right here, the big C in stars. That's just showing that the Celery worker spun up. It's showing what tasks we're connected to here. It's kind of a behind the scenes thing. And then you'll start seeing messages like so. So it's executing step run Pyranda with different parameter values. And that's what you should be seeing here. So then if I want to make sure that this is started, I can check the output directory for this one. And we'll see I currently have 2 that have finished and 20 that are running with 80 total tasks. And so we can keep checking this as we go throughout the study. But for now, I'm going to pass the baton over to Becky to talk more about Sina.
All right, so we've been talking a little bit about these excellent tools we have for, like launching the workflows, launching runs, and analyzing some of that data. But, what do we mean when we say run? What do we mean when we say data? Of course, we're running the simulation. What's that? Inputs and outputs. What's that? Data. It's data tool time. And Sina is one of those. So if you don't mind popping open that window we opened earlier on, where it should be like a Jupyter window, that EC2, and go into Git. From there, we're going to go into Weave Demos. It's easy. Ball bounce. So you can do all of this as well from the terminal. What I'm going to be doing in Jupyter is just so that we can have the interactive visualization component. So we're going to be using the tools that you've used so far through the demo, but we're going to be working with a slightly different little toy code called ball bounce. This is just going to run really, really quick. This is going to be a little side thing that we're doing while the Merlin workers do their thing. So a little quick background on this sort of microcode we're running. Let me pop open. We should have start here.ipynb. And so you can read along or listen to me ramble a little bit. But we're going to be running ballbounce.py. You can probably guess what it does. It bounces a ball around in a 3D box. The physics are definitely not particularly advanced here. This is just meant to run quickly with something that we can kind of take a look at and understand intuitively what's going on. So, you can vary where the ball starts. You can vary the initial vector of velocity. You can alter the gravity, the size of the box, things like that. Okay, where does Sina come in? Well, if you've worked on various simulation codes throughout the laboratory, you might have seen that some of them output a Sina.json. And I'm going to ramble about what that is in just a second, but let's start our own simulations cooking real quick. So this is going to be, again, a proxy for whatever you might be doing as part of your usual tasking. So if we move over to, and again, if you've got the terminal in Jupyter or you would prefer to do this just on the command line, there should be readme.md with this command in there, and it's going to just be this Maestro run ball bounce suite.yaml pgen.py. So we've done a little bit of this. We're going to be launching Maestro. We're going to be launching 10 runs of this toy code. If you want to pop open pgen, you're going to see that these 10 are going to share a starting position, but they're going to differ in their initial velocity vector. Okay, so Sina, what the heck is Sina? Why do we care? What are we doing with the data here? And what is that Sina.json file you might have seen floating around? So notionally, the idea, of course, is that we have a pretty wide variety of codes, and just in science in general, we have a very wide number of output formats, output sources, places data is coming from. And all of those, the way that the data is formatted, it's formatted for a reason. An ASCII table is very easy to scan with our eyes and understand the relationships between columns and rows. A log is going through time. We can understand this linear promenade of events. But a lot of what we're doing in this tutorial is all about scaling up. We're not running one run or 5 We might be running 10, 100, 1,000, and at some point, our eyes aren't really enough. We don't want to look at 5,000 runs as logs to look for one line. So, you have to start turning to like grep. You need to be able to crunch this data somehow. And those scripts, that can absolutely work. Nothing wrong with that. You can do great workflow, working off of like grep and Perl scripts. But there is like, is this portable? Does it work between data sources? Probably not, because it's specific. Is this something that is going to be, fragile over the long term? Can these output formats shift? So there was kind of this idea, like a couple years back, of like, what would it look like if we defined some sort of standards to which, data was formatted? The common file output format, we come up with this like JSON specification, and it's not like, oh, every run has a velocity. It's more like, if you write a library data, how is that formatted? If you have a 1D list of numbers, how is that formatted? If you have this or that, curve sets, time series, how are these formatted? How do you relate the independence and the dependence? So Sina, where it kind of rests in all that is that that's an instantiation of that idea. So we talk with the code leads to come up with this is a general form of data. And then we provide the API that says, hey, include this in your code. You don't need to actually know the raw implementation. You don't have to write open brace, close brace. You just call add data, add time series, add library data. And it kind of just separates out all of the munge of what does that data look like. You on the user side, you're also separated out from that by an API. So in theory, if the format ever shifts, any tool that you write that uses the Sina file, you're insulated from. And we're going to be looking at that today. So if you do ls now, you might see this output.SQLite. So what's happened is we run the ball bounce suite. We run this test code. Fun fact, just to make it a little bit spicier, I actually wrote ball bounce to not output the Sina format at all. It actually outputs a generalized DSV, so I can provide you guys with this very general converter, because again, this whole notion of the common output format being descriptive rather than prescriptive. So what's kind of happened behind the scenes is that Maestro has launched 10 studies of this code. It's output some DSV, and then it's run this ingest command. It said, okay, take that DSV and munge it into this common output format. And you don't need to know what that looks like. You don't need to know the logic behind that. It transforms it into a form that Python can work with, that we provide this nice API for. And there's so many, that's kind of Sina's job, is this huge suite of utilities that you get if you're willing to work with that JSON file. So, we're going to see a little bit of PyDV. You can take Sina files. You can have, without any sort of background information or database architecture, we integrate with Launchit. So, hey, do you have 5, 10, 20 people on your team who are all writing results and want to be able to look at one another's results? Well, that common output format, there's a super simple tool for just taking it into a MariaDB. And now everybody can be writing to the same place and viewing those results at the same time. If you have two different codes that are, both able to output Sina, you can talk to somebody who is working with a data source and understand what you're talking about when you say, oh, this is formatted this way. Tools can be portable. And that's what we're going to be looking at, is just how portable this can get. So that output.SQLite, the reason why I bring it up in the first place is that you are not going to do these commands because, they're a little wild. I cannot type when people watch. So all of this information that you've done in your runs, in your code, in your simulations gets expressed in this format that behind the scenes, Sina can put into all these different styles that make it very, very quick to query. So you get the power of relational databases, but you don't need to know SQL. You just need to know Python. You get the power of transportable data, but you don't need to know the schema. You just need codes that are willing to use this API. And you don't need to trust me on my ability to come up with a good format, because the API is kind of divorced from it. So at the end of the day, you see the Sina file, think, yes, automation. Yes, this was made to be easy to both read and to write tooling around. And yes, that tooling might already exist. So again, hopefully we're just here to kind of make your life easier, and we're going to look at that now. So this is where we get into the visual component. So start here, .ipynb. Again, it kind of describes some of what this simulation is, why we did it, how we did it, what pgen is. But now that it's complete, we have some data to take a look at. visualization.ipynb is going to show one example of that. So again, the whole point with like the SINA files and all of that is that there's already tooling that you should be able to pick up and just get going. Add that magical Maestro step. You don't even know how SQLite even works. You don't even need to know it's a SQLite style. You could use MariaDB. Used to have like some Cassandra stuff. If you're interested, let me know. Point is, you run this. It's just a couple lines of code, and you have an interactive histogram. So this one-to-one, you could do this with like a code that you're using that like outputs, you know, the Sina.json. You're probably going to have a different value that you want your initial histogram to rest on. And you're probably going to have, you know, it might be like my code rec or something like that instead, just to tell it what it's selecting from. But all this other code is completely shared. So we have, you know, this is a visualizer component with a couple lines of code. You can start interactively exploring your information, and we've done this for like, oh, do you want to look at the performance over time for codes? A really common thing, you know, inputs and outputs. Do you want to say like, okay, if I change the version of the code, do my outputs shift? You know, if I have this input, if I have like this model, if I have this or that, how does this affect things? So what I'm going to be showing is these very basic, like baked in create scatter plots. We can also do some more unique stuff. For example, that one's less fun. I'm going to do this one instead. Okay, I told you that all of these start from the same position. This is like the 3D spinnable little, how did our balls differ after that, based on how or when they were launched. Because Sina is, again, like this output format that can work with relational DBs, if you want to pop back over to the terminal real quick and just launch those studies again, launch that study Y. So when that stops running, you know, we're going to be able to look at, you know, the data, but more sets, you know, run more things, add more runs, pile all these things together. And, you know, the more you do, the more powerful this can kind of become, because it says like, oh, you have 1,000 things. Give me the top 100 for, you know, this scalar. Give me everything where the laser package was on. So there is also, while that's running, I'll show you very briefly what some of that query syntax can look like. Because again, the whole idea is that this should be immediately available. You should be able to post-process, do stuff like that, without needing to know, like, this is SQL, this is how database architecture works, this is the underlying schema. So for that, we're going to actually go to Python, user, apps, weave, and demo Sina queries. And we're going to point that at the output.SQLite. So if you were to run that, that'll actually just give you some summative quantities. That's every run that you've done, sucked up, spit out real quick, no grep required. And you can get some summary quantities like, hey, how many runs you've done, you know, what your highest velocity was replaced with a scalar of interest. And if we actually look at what that looks like, you're going to see, you know, it's not going to be that SQLite query like you saw me doing. It's actually just going to be really, really basic Python. So for example, we've got like, you know, you can probably guess what find with max does. Finds the maximum value for x velocity final that we got among all of those runs. So yeah, this was absolutely like a fly through the, again, the point of Sina is that it's a toolbox, and it's a toolbox that you can use to take your simulation data and immediately start playing with it in Python. You know, don't need grep, don't need Perl, and it should be highly portable. You know, like we've got the launch it in a terminal, launch it in a window. You don't even necessarily need the Jupyter, but AWS does not like X forwarding. We're not going to do that. So as just kind of to leave you with, I'm going to show you PyDB. Let me see if this is, have you completed, little guy? So, all right, it looks like we might have like more of that data now. So this is, you could do kind of a dashboarding thing working off of Sina. So we've got, you know, we've run it again. We have 10 more runs. Because every time we run that pgen, we get, you know, another set of 10 that have the same spot, but different vectors. So again, with hopefully very few alterations. Oh my gosh, yeah, it helps if I remember what strings are. All right, that's what another run looks like. Highly portable. And you can, again, like use this sort of visualization for anything you might be doing. This is all proxy stuff. Finally, I'm going to show a little of PyDB, but we're going to have like a proper PyDB section, I think, later. So this is really just more to say that, like, hey, PyDB takes the Sina files as well. PyDB's demo Sina.json. So you see the Sina file, think automation, think like, okay, I can use an API to start post-processing on this immediately. Please play around with it a bit. And with my bit done, Jorge, do you want to tell them a little bit about what more you can do when you add Kosh on top?
Okay, great.
It's small.
So yes, as Charles mentioned earlier, we have another database tool called Kosh, and Kosh is built on Sina. And the capabilities that are added for Kosh is that it has loaders, transformers, and operators. Loaders are objects that, as the name suggests, load files in any format, so it doesn't have to be in that Sina.json format. It could be a CSV file, it could be HDFI file, it could be whatever you want. Transformers takes that data from whatever format and modifies it however you want. So maybe you want to take the average, the multiply it by 2, whatever mathematical operation, and then operators is a step above transformers where it takes 2 data sources in whatever format they are. It could be different format, or it can be an HDF5 and what can be a CSV file, and then combines them and does whatever mathematical operation you want on them. So those are the 3 main features that Kosh adds to Sina at a high level. So now, if you all open up,
slightly bigger, please. Sorry, it's just really
sorry.
tiny. It is to me.
Is that better?
Yeah, that's better. That's great. Thanks.
Okay, sorry about that.
That's okay.
So yes, if you all could open up the Start Here notebook. Becky just went over this, just the command line of the bounce ball CSV or bounce ball program we wrote. And then, so now we'll go a bit below, and then we'll need to import Sina just because we'll use it for one of the filters later on. And then, so now we have Kosh. So it's the same syntax. You know, we have our store, we connect it with Kosh, we have the output SQLite, which we created earlier from the Maestro ball bounce study. And then we just want to find how many records are in that. So store.find without any arguments just gives everything in there. Let that load. Okay, so then here's where we use one of the Sina filters. So find with max, as Becky showed, we want to find the data set, the record with the number of bounces, and only give me the first top. If you put 2 or 3, it'll give you the first, the second or third top, the top 3, sorry. And then we print the data set, and here we see the attributes. So the length of the box, the gravity, the group ID, X position, final, initial, etc., etc. And then afterwards, we could, if you want to add more attributes, it's pretty easy. You just assign them. So the data set that we acquired before, we create a new attribute just called my new attribute and make it equal to 6. And now the data set has a new attribute along with all these other attributes above. And these are the attributes you could use to filter data sets out. So then now, features in Kosh are curve sets in Sina. So these are just time series data. So attributes are individual items. There could be strings or floats or whatever you want. But curves / features, as they're called in Kosh, are actual time series. So here it's pretty simple. We list our features, and then we say we want the first 5 values of the physics cycle series / time. So then we just print it like that. So now here we're going to create an example HDF5 file out of the data, out of these features we have up here. So it's just going through each data set in the store.find method, and then it's grabbing the X position, Y position, and then calculating the velocity, and then creating a HDFI file and filling in the HDFI file. And then at the last portion, this is how we use loaders. We associate files. So here we're just associating the file, giving the URI, and then telling it what type of file it is. So in the backend, we have some default loaders. We have HDF5, NumPy, JSON, and we also have all the pandas read functions. So read CSV, read Excel, etc., etc. So you could associate a bunch of different files, but if your file is unique or has a different type of format, you could create your own custom loader. So there's no need to worry about that. So now if we print the data set and its features, we see that we have that file associated with this data set. So it's important to note that the file doesn't get absorbed into the SQL database. It just points to it, and then through the Kosh, the backend, it's able to grab those features. So if you do list features again, we not only see that we have what we had before, but then we also have the speed, X velocity, Y velocity, and Z velocity from the actual HDFI file. So now that we have those extra features, it's as simple as before. We just say, give me the first 5 indices of these 2 features. So here's our HDF5. And through the loaders, it knows in the backend how to grab that data. So there's no need for the user to modify anything. So it's simple as that. And then we could also create ensembles, which this is how you group data sets together. So it's just an easier way to organize items and then search for data sets within the ensemble as well. So now here, we created our Kosh ensemble with create ensemble. And then you could also assign attributes to it. So now we have our Kosh ensemble and its attributes we just made. And then here are all the data sets that are associated with it, because we just did a for loop, which we did ensemble.add data sets. So these are the 10 data sets we created earlier through the Output SQLite server database. And then we just print our ensemble, our data set attribute. Since it's part of ensemble, it acquires that attribute from the parent ensemble. So now the data set has that attribute, a group attribute from the ensemble. And then here, since these ensembles are grouped, we're using the find method within the ensemble. So we fine tune our find criteria pretty much by searching this subset of data sets. And then here's where we use the Sina searching utility from before. So we're trying to find the number of bounces that with a minimum of 6. And then 9 of our 10 data sets have a minimum of 6 bounces. So then here's our custom operator, which allows a user to perform mathematical operations on data sets that have different formats. So here we're just doing a simple average. We give it the decorator NumPy operator, Kosh NumPy operator. So then now it's taking the average of all the data sets of the feature speed within those data sets. And then here we're printing the average speed to the first 5 values. And then now here we're just creating another file that stores the average speed above, and then we're associating it again at the ensemble level. So you could associate files at the ensemble level as well. And then here we have the printout of the ensemble and the associated HDF5 file we just created. So yeah, as a summary, loaders, transformers, and operators are the big 3 things that Kosh added to Sina. Loaders, you could load any type of data. It doesn't matter what format it is. Kosh has some in the background that are there by default, but then you could create your own custom ones. Transformers operate on, I shouldn't say operate because that's the name of the other thing, but transformers transform the data of a single data set and then operators operate and transform the data on data sets from different formats or the same format. So in conclusion, Coach has some pretty cool things, especially this associate file level. That way you don't have to look for the file and absorb that data. It does it automatically for you. So that's it for my section. I'll hand it over to Xiao for the VBUQ portion of this presentation.
So we have already got all the simulation data and the results, and we're going to briefly introduce what is the Bayesian inference. So in this slide, let me briefly talk about what is the Bayesian inference, and to demonstrate it, we will use an example of the blind man and the elephant. So it's an old story. So we start with some initial beliefs. So imagine that several blind men encountering an elephant for the first time. So each blind man touches a different part of the elephant. Let's say its leg or trunk, and they might, have some initial beliefs that on what we call the priors based on this limited evidence. So for example, one might think, oh, the elephant is like a pillar, and while another thing is like a rope, as shown in the first panel of the picture on the right. So here's what we think about Bayesian inference is as the blind man continue to touch different parts of the elephant. So it's like we are running this Pyranda simulation and we're getting the data, we gather more information. So this process represents what is Bayesian inference. So where they start questioning their initial belief based on some more data they have, some more simulation information they have, some more experiments they did. So they start to realize that the elephant is more than just a pillar or a rope. So they talk to themselves, they talk to each other, they update their beliefs, they have more evidence and experimentation. So their beliefs were going to change and evolve. So they reach a more accurate understanding, recognizing that the elephant isn't just what they initially saw, it's something larger and more complex. So at this point, they come up with some better understanding we call the posteriors. So finally, after considering all this available evidence, the blind men update their final belief. So this posterior correctly identify the animal somehow, maybe never be able to know that is the elephant because they've never seen that before, but they made a better understanding. So it's something more complex than what they thought. So it's similar to an elephant or something like that. So this can continue to evolve to more real elephant, if possible. So as we collect more data, collect more simulation, collect more, communication with the likelihood function or how similar to observation, all those kind of conditional probability. So in summary, Bayesian inference is a method where we continuously update our beliefs as we gather more evidence. So leading us to a better understanding of the truth. So in the next slide, Renee is going to talk about the experimental design and what is the detailed understanding of the Bayesian inference. Thank you very much. So I'm just going to shift it to Renee.
Okay, thank you, Xiao. So this is a little bit more detail about how Bayesian inference is involved with our UQ study today. So our uncertain parameters in this case are the Atwood number, velocity, and some noise represented by sigma here in the green squares. And we also have some data that we've collected that will inform our understanding of these inputs. So we have experimental data of the mixing width and simulation data. In this case, we're going to use a surrogate model to emulate our simulation data. And we're going to use a Gaussian process model. And the goal is to find the posterior distribution. But since that calculation could be complex, we're going to approximate it with Markov's chain Monte Carlo or MCMC sampling using our IBIS and pSwade tools. And so those will do the work to calculate the likelihood and multiply it by the prior distributions. The prior distributions are our understanding of our uncertain parameters, Atwood number, velocity. If we don't have a good understanding of those, then we can use an uninformative prior distribution, for example, uniform. And then from our posterior distribution, we can better understand the distribution of our inputs. So we'll be able to combine our information and have better informed distributions. Okay, and so we should have generated a lot of data with Merlin in order to train our surrogate model. So are we checking on that?
Yeah, Brian, you want to?
Here, let's just clean this up just a little bit. So if we check the status, we will see, yeah, everything's in the green. We're all done running. So now what we can do is we can look at the output workspace here. So the path to this is shared data, RT studies, or Rayleigh-Taylor studies. And then the one that we are looking for is, oh, there's multiple. The 241 right here. So as I mentioned before, we have, a subdirectory for each of our steps and everything. The UQ part of this is the final step, the Bayesian IBIS. So we can take a look at what's in here. Let's see. So the .sh script will show us exactly what was run. If we take a look at that, it's just showing that we fired off the script that does this. The .out has the output from this. And so it's showing we did all the sampling's done. And then the .error would have information if we needed it from any error that occurred. Charles or Renee, is there anything specific you wanted to look at here?
I just wanted to mention that we, if you look at the file that we run, like the plot data and the Bayesian, we embedded Coach and Sina in them. So we didn't have to know the timestamp and everything of the directory where the files are. So like, I think it's in, can you look at, which file are you looking at here? Sorry.
Oh, is that plot study?
Okay, so in plot study, you can look, we're opening the store because from one of the steps of the post running Pyranda was to put all the JSON file into a store. And so we're just opening the store and instead of doing something like on the line above, we don't have to know the timestamp, we don't have to, we just open the store and then, okay, here we're creating an ensemble so we can put all these things together as we're demonstrating. But here, that's, yeah, right there, like we get the time, but I would just say like, okay, get us the time and the mixing width, and we don't have to know where any of these data and Sina files are. We just grab the data automatically. And then we, at the end of that, I think Renee is creating a new file for the Bayesian study and is associating that with the ensemble. And so, and then the next step, the Bayesian will just go grab that URI.
Right, so
that
again,
we can do it another way.
Yeah, we're just connecting to the store again and
yeah,
finding
we're
the
opening the store, we're getting the ensembles that match. And yeah, URI right there at the top. Experimental URI and sim URI, and like that, we don't have to figure out what the timestamp was and everything. It's all stored by Coach.
Right.
And you get us the data. And then, but now we can move on to the actual UQ part, yeah.
Okay, should I stop sharing then?
I think so, yeah. I don't know, is it Xiao or Renee now? Forgot.
Next slide, we're going to show that if we use a software called the P-Suite developed by our lab, and as an alternative way of doing the UQ analysis, so we have generated two input to one output results, and this is the data we have. Then we have some experiment data, and we're going to show how we're going to use the one kind of Gaussian process to approximate this data set. So to do that, so we have go to that. So yeah, just the one above the RT studies, which is in this directory in the shell data. So we have a README file here. So we could just say more README, and we're going to see everything here. So the first step, we're going to start one UQ engine. which is called pSuite. So it's going to read data and save data for UQ analysis. I start that on the left-hand side. We press enter. So we enter the pSuite environment. So right now, this is the light version of pSuite. It's not the latest version, just for demonstration purpose. So when you just hit very simple thing, just called H, means help me to see what kind of ability over there. So for the first step is we're going to do it like HIO, is for input and output. So it has a bunch of command over there to help you to read a file. So right now we have a file called the data simulation data CSV file. So we can just quickly take a look. Okay. Of that, that's the CSV file. So we're going to use the one called read CSV. We copy this one here. We press enter again. So it asked me to use the first line as a variable definition. So we have that, which use Y to tell, okay, that's just the definition line. Then we enter the number of input. So here we have 2. Then this already tell you there's 14 samples, 2 inputs, and 1 output. You can visualize this data using pSuite, but let's skip that step right now. Let's first write the data into the pSuite format using the write command called write. And this file name, which is called demo pSuite data. When we do that, so we can see that we now have these demo pSuite data there. Before we didn't have that over there. So once we have this one, the next step is we can actually take a look of what this pSuite data looks like. We just do the mole. So it gives you a lot of samples and give you the information. So it goes to give you the range and tell you any kind of like sampling strategy you can use, but you don't have to go through this data file to do any specific job. You can just modify that in the pSuite interface. Okay, we're going to skip that for now. So let's go back to the README again. So the next step is once we have this one, we're going to do the response service for GP prediction to check how accurate. So one kind of response service we're going to use here, how accurate that is. So the first step is we're going to load this data again into the pSuite. Then we do the RS check, which is response surface error check. Now I'm going to show you a bunch of the options you can use as a surrogate model to test the accuracy of the response surface. So here I did many one, and I found this one is pretty good job for this particular task. We just choose the number 8, then press enter. Then we choose output number, just by default is 1 because we only have 1 output here. Then it's asking, do we need to perform cross validation? Yes, because using that, it can help us to do the training data testing to see how accurate of this data for the validation. We press Y. And so here we're going to choose the number of groups for validation. So the more group you choose, the less number you have in each group. So that means it's more difficult for basically the approximation from a surrogate model. So the last group you choose, you have more data for training and testing. So it's easier to get more accuracy. Since we only have 14 data in this tutorial, we just choose a small number of groups to inform the accuracy. Let's choose 3 for this test case. Okay. Then with asking, do we need to do the random selection? We can do that. But if we select no, then we don't have to repeat the experiment again. It's not repeat. It's no repeat repetitive. Okay, just choose Y. Then the pSuite will automatically generate a file for you. It's called the ISFA CVER.OM, which is a meta file. So if you try to visualize, just to look into that file, you're going to see they already have this a lot of the data and the MATLAB command already. You can just run this MATLAB command, and then you can visualize the solution, which is right here. So this the solution looks like. Then this is the another one we can use pSuite to do, but I'm going to skip the steps but there's some command over there can help you to do the similar job, like the standard deviation for the surrogate model solution looks like in 3D and 2D case. Then in the next example, we're going to show you how we're going to use the MCMC in the piece weight format. So on the left-hand side, we have the the observations. So we have two design variables, and we have one output. The 0.1 here basically tell you the accuracy of the observation. So this one we have 10 observations. We have the mean value, and we have the 0.1 accuracy. We have some input corresponding to the output. We're going to use this one as the observation to see how can we drive piece weight to infer the solutions. To go back to our question right here, going to look at the README file again. So the next step, we're going to do the MCMC for Bayesian inference. After we have already checked that response surface that we selected that GP is good, we're going to use that specific GP that we have already done as a surrogate to do the Bayesian inference under the MCMC framework. So to do that, we're going to first look at how the MCMC file looks like. So this one basically tell you that is the likelihood function we're going to use in the piece weight format. We have begin and end. Then the next step is the same again. We go to the piece weight environment. We do the load. Then we have everything over there as well. We're going to just use this one simple command called ISMCMC, which is response surface-based MCMC. Here we have the surrogate model that we chose, which is the Gaussian process, which has pretty good accuracy as we have tested the cost validation. So everything is clustered on the diagonal line. So that means the accuracy is pretty good to use this surrogate model. So once we hit that, the environment's asking us what is the name of the file to do the likelihood function. So we have already put it here. We just copy this one and put it here. So then we have a lot of options. So what kind of the surrogate model we can choose. So yeah, we can choose here, or we can even modify the data file we had before. But for the demonstration purpose, we just choose here again, which is not necessary. So that has already been specified in the data file, or you can actually manually specify that by yourself. You don't have to go through this environment by yourself, okay, manually, okay. Then we just do the number A again. Then this is a simple version. It's just using the brute force MCMC, and it also has the better version in the latest release. Then it has the basically the natural Hedges posting, and also has the Gibbs sampling. But this one just using the brute force, and it works okay when you only have one peak, one model of the experimental data. If you have a multi-model, then this one may not work really well. So again, it tell you what is the solution looks like that maximize the likelihood, based on the experimental data you provided and the response surface you provided. Then they generate the MATLAB file here. We can just take a quick look of that MATLAB file. So that just basically tell you everything you have for the inverse solution. Then, so this one we just show the solution looks like. So we start with some uniform prior knowledge, has no understanding, and based on everything we have, and based on the very accurate observation in something very close to prescribed input variable with a little bit noise, and we can basically doing the sampling and under the Bayesian inference framework to recover that it is actually correspond to the solution. We think that is the highest likelihood we can have. And so this solution for these two inputs looks like, and joint distribution looks like. So starting from no knowledge of that. So for the next, we're going to hand over to Renee to talk about another ways of looking into this surrogate model and Bayesian sampling. And thank you. I'll just stop here.
So we already saw how we connect to the Coach store and access all of the data in this So I just wanted to show how we train the Gaussian process model on our simulation data. And I created some plots. So this is showing the prediction for the mixing width over Atwood and velocity values. And the color is the standard deviation for the prediction. So in areas where we trained our model, it's a very low standard deviation. And I forced the model to predict a little bit outside in these corners. You can see that when it's forced to predict outside of the training data, then the error increases. And then I also created a plot for leave-one-out cross-validation. We're training a model on all of the data except the first sample, and then we do that with the second sample also. And so we train models, we train n models for n samples, and then we can understand the actual value compared to the predicted value by our model, and it's predicting very well. And I also plotted error, 90%, 95% confidence interval error bars, and those are so small that we can't see them. So it's predicting very well, and so we can trust our Gaussian process model to emulate our simulation. And then in the Bayesian inference, this is the same code that you'll see in Bayesian inference.py in the repo. So we're going to use IBIS this time to do the MCMC sampling. We use our default MCMC object. First, we need to provide the input information and the ranges for the inputs and estimate of the standard deviation. We provide all the output information to our object, and then we have our MCMC object, and we call run chain, given all of these attributes, and then we can plot the results also. So this is showing good mixing, and in the end, we get our better informed distributions for the Atwood number and velocity. And then we can use those better informed distributions to create better predictions with error bars. So this is a pretty easy way to run MCMC sampling and do our UQ study.
Thank you, Renee.